So, hello everyone. My name is Swastik Soni. I'm the PhD scholar in the Department of Metallurgical and Material Engineering, IIT Ropar, Indian Institute of Technology, Ropar from India. So, I am presenting on the topic the quantitative factography in the DBT regime, ductile to brittle transition regime of 9 chromium, 1 molybdenum steel. Because yes, 9 chromium, 1 also said P91 steels. So starting with why quantitative factography. Basically factography is this is the part of material science which determines the cause of failure in the materials. And quantitative factography can also be used to evaluate the performance of the new materials under various loading conditions, helping to improve their design and manufacturing process too. In case of fatigue, the quantitative factography allows the precise measurement of striation spacing on the fracture surfaces. And by quantifying fracture features, the engineers can better understand the root cause of the material failures, whether due to the overload, fatigue, corrosion, or by the environmental stresses. So here are some of the microstructures which can explain this is by the fatigue due to due to striation spacing, and this is having the bright facets. So this is maybe brittle failure, and this is through tensile. Next, the background of 9 chromium, 1 molybdenum steel, or we can say the P91 steel. So here the analysis of P91 steel reveals the critical insights into the failure mechanics under the ductile to brittle conditions. Understanding these mechanisms aids in the predicting material performance, enhancing design strategies, and improving safety in high temperature applications. But in this case, we are using to find out the find out its transition in the lower temperature. So this is the microstructure for the steel and the chemical composition for the same. So here we have some of the results on ductility at the different strain rate and the temperature. So in this graph, we can see that the effect of ductility at 0.5 mm or the lower strain rate. We can see that at the -20 degree temperature, the brittleness is lower, and when we decreasing the temperature, the effect on the ductility also changing. So while increasing the further more temperature, more strain rate, what we find the similar results like at -20 degree, the ductility is less, and by increasing the by decreasing the temperature, the ductility may increasing. And by increasing more strain rate to 10 mm per minute, we will find a transition here that at now at the brittleness at -20 degree is higher respect to the -40 degree temperature. And while increasing more ductility, more strain rate, we'll find the same results as on the as here. The temperature at -20 degrees is more than the -30 degree. Next, comparing these results with the yield strength and the temperature, as we can see here, at the lower temperature, the yield strength is higher, and once the temperature is increasing, the yield strength is also decreased. So similarly, the effect on strain rate, it is not the linear. We have the transition at around 8 to 12 mm per minute. Next, coming to when we compare it to strain hardening exponent, which is calculated through a Ramberg-Osgood equation. So, the fact is with the temperature, when the temperature is decreasing, the exponent will increase, and with the strain hardening exponent and the strain with the strain rate, it's have transitions. So here we can see that the fractal dimension and the microstructure by we can see that at the highest temperature and the lower the strain rate, we can find the more brittle in the microstructures. And while we taking it to the lower temperature, with the higher temperature and the higher strain rate, we can find the opposite. We find the ductile microstructures. So these are the few references that we have seen. Thank you. Any questions?